Good afternoon and welcome to the Administrators Seminar Series. We're here once again to discuss the nation's future in space. This is the fourth in a series of dialogues that looks at different aspects of what might comprise a driving goal for the next era, a goal that's fundamental in character and that's important to the public that supports the space program. Martin Luther King said, "As marvelous as the stars is the mind of the person who studies them." And so when we began this series in January, we started with life. What does life mean? How would we recognize it elsewhere, either in our own solar system or on another Earth orbiting a distant sun? The mind of the person who studies the stars created cosmology. By virtue of this activity, we put ourselves squarely at the center of the universe, looking outwards. This theme, life and its self-conscious exploration of itself and the cosmos, formed the basis of our first three seminars. Today's seminar is called New Frontiers in Climate Research. The refrain from Lynn Margulis, the speaker at our first seminar, runs through today's too. Life is a planetary phenomenon, she said. The images we have gotten back from our shuttle missions show clearly that climate and its change are a planetary phenomenon. Life thrived in abundance without self-awareness for perhaps 3.5 billion years. Yet in our much briefer history on the planet, we have transformed it. What is the impact of the climate on climate of our own actions? And what is the interplay of our doings and that of nature's? How do all the different aspects of climate research fit into one overall planetary picture? Understanding this has motivated a U.S. global change program, and NASA's part of it, which is called Mission to Planet Earth. Today we're going to hear how science and space contribute to this mission, and our distinguished speakers, Dr. Ellen Mosley-Thompson and Dr. Michael McElroy, will address the question of what should be our long-term vision for monitoring the planet and communicating this information widely. I'd first like to bring up the NASA administrator, Mr. Dan Goldin, whose vision shaped these seminars and whose leadership propels us to consider a future beyond the '96 budget. Mr. Goldin.
I was recently in a set of discussions with some of the people from Robert Mondavi wineries, and they have a problem. It's called phylloxera. It comes around every 100 years or so, and it wiped out the grapes in France, and it's now in the process of beginning to destroy some of the grapevines in Northern California. It's very interesting about phylloxera. When you're on the ground, you don't see it. You don't know that it's beginning to destroy the plants down in its root system. But from the height of space, you could look down with a hyperspectral device, and you could actually see the stress on the grapevines from the phylloxera. So what this tells us is, when you're close, you can't necessarily, they say you can't see the forest from the trees. Space gives us an ability to holistically look down on our own planet and get a sense not just about what's happening in this spot or that spot. We get a broad, holistic view of our own planet, and it touches everybody's life. And as we have 5.5 billion strong on this planet, preparing for as many as 10 billion, perhaps in 30, 40 years from now, it's very, very important that we understand the forces of nature and we understand the forces of the human species. And right now, most of the debate that takes place with regards to our environment is based on passion and emotion and who could print the most, who could get the best press bite. What we'd like to do is have rational decisions about our environment, about our own planet, and how we manage those resources. And that could only come with a holistic view. So we are set out on a course And we only see maybe 5 or 10 years out on this course, but let me take you out 20 or 30 years to what I think we could have. I think we could have virtual coverage of our own planet that's active and passive coverage, multispectral, with a armada of small spacecraft hooked up either through photons or through RF waves, so they're coherently coupled so we could get pixel registration, that will allow us to understand the stresses on our life forms, the stresses on our planet, so we could understand how to make rational decisions. At the same time, when we have this wonderful data, we could close the biological circle. People are very, very isolated from nature today. And I've said this before, you know, in big cities like Washington and New York, you know it's fall, not by when the leaves fall off the trees, but when the football season starts. And you know it's spring when the baseball season starts. As technological as we are ecologically isolated from our own environment. So by having this ability, which technology could give us, it should be able to close the loop. But towards what purpose? Are we going in the right direction? And this is what I think we'd like to explore today. The why and the what, not the how, because this is what we concern ourselves with at NASA too much. How are we going to do it? How many spacecraft? What will it look at? So we'd like to explore the what and the why, and then understanding the what and why of the problem, we could get to the how. So I look forward to the discussions today.
Thank you. Okay, our first speaker to talk about the what and the why is Dr. Ellen Stone Mosley-Thompson. She received her higher degrees in climatology from Ohio State University and is now an associate professor there. She's also a research scientist for the Byrd Polar Research Centers. One of her specialties is paleoclimatic reconstructions based on evidence preserved in ice cores from Antarctica, Greenland, China, and Peru. She's been involved in global reconstruction of the Little Ice Age event, the role of volcanism in the last millennium of climate variability, the reconstruction of abrupt changes in the environmental system, and the impact of these changes on human activity. She has served as a member of several National Academy and NRC committees on global change in the environment, and is currently president of the Atmospheric Sciences section of the American Geophysical Union. Dr. Mosley-Thompson.
Thank you, Dr. Cordova. And thank you for coming, and it's quite a pleasure to be here. I'll start with my first slide. The title of my talk is Ice Core Records as Windows on the Past and Keys to Our Future. I like to start my talks with this picture. This is the margin of the Quelccaya ice cap, which sits in the Andes of Peru at 14 degrees south at over 6,000, or at about 5,700 meters. What you see here are the annual layers. Each of those is the snow that accumulated in a given year. I'll come full circle. At the end of the talk, I will show you how this ice cap no longer looks this way and is no longer preserving this unique archive. If we drill through ice caps and ice sheets, we get an ice core, much like this, drilled here using a thermal drill. I showed this. Some people might not know what an ice core looks like. This slide outlines the type of environmental data that we get from ice cores. The beauty of an ice core is it produces a multifaceted record. It's a cylinder. If we take a cut through there, we get a cross-section like this, and then we can partition the samples and make a variety of measurements. For example, one of the most common measurements is that of the oxygen isotopic ratio, which we use as a proxy for temperature. We can also measure atmospheric chemistry, the dustiness of the atmosphere, vegetation changes, not in the polar regions, but outside the polar regions, the Earth's volcanic history, and as Dr. McElroy will show you, anthropogenic emissions, carbon dioxide, methane, and nitrous oxide. In ice cores where we can discern the annual layer, we can say something about how much snow accumulated in a given year. In other words, we can go back and reconstruct the precipitation history in that region. This slide is busy, but it shows all of the places where we have either had an ice coring project or we anticipate having one. In the next slide, I'm just going to show you the upper 40 meters of a core from the Dyer Plateau, located right here on the Antarctic Peninsula. It's a busy slide. I'd like to call your attention to these two profiles, the oxygen isotopic ratio and the sulfate concentrations. This is just the upper 40 meters of a 200-meter core. I'm using this to illustrate to you how we date cores. Ideally, we like to date them year by year. To do that requires that we discern or measure something that has a seasonal signal. And here in Delta 018, we see summer, winter, summer, winter, summer, winter. We see high flux of sulfate every spring. So essentially, we can drill through, it's like a layer cake, and when the accumulation rate is high enough, we pick up these seasonal variations and we can precisely date these cores. These cores provide an opportunity to reconstruct the Earth's volcanic history. This happens to be the eruption of Mount Pinatubo in '91, and we know that the sulfuric acid droplets have essentially, the cooling in '92 and '93 was attributed to the sulfuric acid suspended in the stratosphere. Well, we can take a record like that with ice cores and go back in time. This again, a busy slide, but the upper two, this is excess sulfate. We have to extract the oceanic sulfate component, and we do that by measuring chlorine or sodium. What we are left with is the excess, and the two prominent sources of excess sulfate are volcanism and the burning of fossil fuels, both of which we see in this diagram. These are the individual eruptions, the spikes. This is Northern Hemisphere, 2 sites in Greenland, and 2 sites in Antarctica. And you can see that although there are many, many eruptions in the Northern Hemisphere, those eruptions that are preserved both in the north and the south are much fewer. I'd point out the eruption of Tambora right here. It's part of this couplet. Tambora erupted in 1815, and it was credited with the year without a summer in 1816. However, if you go back and you look at the climate history, the temperature records, it was found that actually the climate in that decade from 1810 to 1820, the temperatures were actually declining before Tambora erupted. And this was used as evidence against the potential of a volcano temperature linkage. However, with these ice cores, putting them together, we found another eruption in 1809, virtually the same magnitude as Tambora, very outstanding event of the same magnitude in terms of the sulfate it produced in the Northern Hemisphere, but not recorded historically, but well preserved in the ice core. And we speculate that was this eruption in 1809 that really set the stage for the cooling of that decade. And then, of course, adding insult to injury with Tambora, we recorded the lowest, the decade 1810 to 1820, the lowest temperatures on record. When we collect the ice cores from many locations, in other words, we have a diversity of ice core records, we can begin to study different components of the Earth system. Just a brief word about preliminary results. Actually, this was a small project, preliminary, funded by NASA, to look at the ice caps in Franz Josef Land in the Russian Arctic. And Franz Josef Land, located here at 80 degrees north, is the furthest north landmass in that sector. We looked at 5 different ice caps, and we found that on the island of Graham Bell, the Windy Dome ice cap contains a reasonably well-preserved record and is 500 meters thick. Now, I'll give you, these data are very preliminary. We were only drilling with a hand auger. This means we extracted a 20-meter core, so the record does not go back very long in time. But what we found is that increased chloride concentration, chloride is in green, that when chloride concentration is high, the concentration of sea ice in that area is low. So in other words, low sea ice, more open water, a greater concentration of chloride. And the R square, this is only a 10-year record, but the R square, or coefficient of determination, is 0.34. It's pretty good to explain 34% of the variance. And this is just a linear plot of the increase in chloride against the decrease in sea ice concentration. So we're optimistic that cores, particularly from the Windy Dome, may provide a long record of sea ice variability. I'd like to move to the southern hemisphere, to the Quelccaya ice cap. It sits at about 18,000 feet in the Andes at 14 degrees south. This was actually one of the first drilling projects outside the polar regions. Quelccaya sits here. It covers about 60 square kilometers. The local mode of transportation shows you that it is a very remote area. The precipitation to this ice cap comes from the Andes in the form of these convective storms. These are people on the surface for scale, just to show you that once you're up on these ice caps, they are very large. This was the first use of solar power because of the remote nature of the site. It was virtually impossible to drill this in the usual Antarctic tradition, and we used 60 solar panels to extract 2 cores to bedrock. Now, this is the same ice cap in which I initially showed you that vertical margin. And this is what it looks like if you drill through it. These are core sections, and these are those visible dust bands. At 139 meters in the core, we still have well-preserved dust bands. This is what I mean by annual resolution, where we count back year by year. The Quelccaya provided a 1,500-year record from this region, the first record of that length, of that quality, from the tropics. We extracted a history of the dustiness of the atmosphere, the accumulation, in other words, the changes in precipitation, and the oxygen isotopic ratio tells us something about temperature. And I want to focus in the next few slides just on this record, the 018, and this feature here, which is the Little Ice Age, and the precipitation history. On the bottom and the middle graph are the oxygen isotopic records going back to 1600 from Quelccaya. We always drill 2 parallel cores at a minimum. The reason is if you find something unusual in your core history and you cannot replicate it in a parallel core, then you have to suspect that maybe you have an artifact. If you can reproduce it, it gives you confidence that you are reconstructing a respectable history. So you can see the 2 cores give essentially the same isotopic results, but we've plotted those here against the northern hemisphere 10-year average temperatures. And I'd like to point out two things. First, you can see that the general shape of the curves is very similar. Secondly, that this little ice age period, and you'll hear more about that from Dr. McElroy, but it was essentially a cool phase in the Earth's climate history from around 1450 to about 1880 AD, in which it's estimated that temperatures were about a half a degree cooler. Also notice this decade that I've already mentioned, the coolest decade on record, 1810 to 1820, faithfully recorded by this ice cap at 18,000 feet at 14 degrees south. South America is very rich in archaeological history. This happens to be Machu Picchu. In this slide, we've plotted the 1,500-year record of net accumulation, showing essentially periods where we had less accumulation and more accumulation in the southern highlands of Peru. Over here, we're looking at the rise and the fall of the cultures in that area. And I want you to focus on the cultures here in the southern highlands. And we can see that during this time, we have fairly high accumulation, and we have this particular culture, the Hori culture. As we enter this period of reduced accumulation, that culture essentially leaves the highlands. And the cultures that does not return to the southern highlands of Peru until this more pluvial period. And this is actually was the rise of the Inca Empire. And of course, the termination is the entry of Spanish into South America when all of the cultures essentially ceased. What we know is that the cultures in the highland areas and in the coastal areas tend to function in antiphase. That is, when one culture is flourishing, another culture is diminishing. And when I talk about El Nino here in a minute, I want you to remember this. The climate in Peru is dominated by the El Nino, and that system called El Nino Southern Oscillation, or ENSO. Essentially, during ENSO, we get drought conditions in southern Peru and flooding conditions in northern Peru along the coast. It just happened that the drilling project on Quelccaya, the big drilling project, occurred in 1983, in the middle of the mega El Nino of 82-83, the largest ENSO on record. On this side, we see the Quelccaya ice cap as it normally appears as it appeared in 1978. These are people for scale. This is the same shot taken in 1983. And you can see that essentially the drought in that area is taking a toll on that ice cap. This is just a very short record of the annual layer thicknesses. Essentially, what we found is that during the ENSO, the accumulation rate on this ice cap drops by at least 25%. This is the 82-83 El Nino and the 76-77 El Nino. So we were encouraged that the ability to reconstruct these annual layers and their thicknesses might allow us to reconstruct a much longer record of El Nino Southern Oscillation for this region. And in fact, we have here the last 500 years. It's a very, very busy slide. And we have plotted here the El Ninos as reconstructed by Bill Quinn back to 1500 AD. To make a long story short, we essentially found that most of the ENSOs were recorded in Quelccaya as thin layers, but we had more thin layers than we had ENSO. And if you think about it, it makes sense in that there are many other reasons why you would have a year with reduced accumulation. Later, I'll show you I'm not going to follow up on the INSO part, but we've just completed a project in northern Peru. In the previous slide, remember, northern Peru gets more accumulation. So we now hope to put these two records together, matching in the south thin years with in the north thick years, and see if we can better calibrate our current ability to reconstruct El Niño Southern Oscillation. Ice cores also have the ability to provide us a long-term perspective. And this perspective is critical if we're going to understand the natural variability of the climate system, and we must understand the natural variability if we're going to separate it from recent anthropogenic effects. We all run up against this all the time. Well, how do you know the 20th century is unusual? How do you know that the 1980s were unusual? The only way you know is to look back through time and use that history as a measuring stick. I want to move now from Kelkaya across the Pacific Basin to the Tibetan Plateau. Now, I would just point out this is a NASA image taken, I think this is November of '82, and you see here the Pacific Warm Pool. In Asia, the dominant climate system is the monsoonal circulation system. And the monsoonal circulation system is driven primarily by the intense heating of the Tibetan Plateau. The Tibetan Plateau is the most outstanding feature on the Earth. It has an elevation of over 4,500 meters, and it contains over 60,000 square kilometers of snow and ice. This is the Dunda ice cap located in the on the north central part of the Tibetan Plateau. For scale, this is a party with horses going to the summit. The Dunda ice cap it epitomizes what we call an ideal ice cap, shown here in a schematic. And what we look for in these drilling projects are dome-shaped ice masses with relatively flat basal bedrock so that the flow regime is fairly simple. But for any ice sheet, ice cap, there are three things that determine the length of the record that you will get. The first is the amount of accumulation that falls. The second is how thick is the ice. And the third is whether that ice is frozen to the bedrock. Because, of course, if it's not frozen to the bedrock, you're losing your record from below. In theory, were your ice cap frozen to the bedrock, and had it been so throughout time, the first snow that fell in that region theoretically should still be there. We know, however, that it would be thinned infinitesimally small and could not be discernible. But the idea is you want to look for ice caps frozen to the bed. The oxygen isotopic record that I've been talking about, we use delta O18 as a proxy for temperature. And I just want to show you, because we have had this long-term collaborative project in China, we have the ability to have snowfall collected and the temperature measured at the same time, contemporaneously. This is something that is very difficult to do over the polar ice sheets. Essentially, we have the delta O18 here and the temperature. We have more negative delta when we have colder temperatures, less negative delta and warmer temperatures. The Dunda ice cap contained a record well over 40,000 years long. This was a surprise to us, actually. We had anticipated a record maybe of 5,000 to 10,000. The Dunda cores represent the very first ice recovered outside the polar regions that contain ice deposited during the last glaciation over 12,000 years ago. But more importantly, it provides that backdrop or that measuring stick. Let me use this to illustrate. This is a 12,000-year record of Delta 018. More negative is cold, and what we see here is the end of the last major glaciation and the overlying Holocene. The shaded area represents the Delta 018 average for the last 50 years, 1937 to 1987, the year we drilled the core. As you can see, the last 50 years have been the warmest in the last 12,000. Now, climate models, which we know are imprecise and imperfect, and Dr. McElroy will mention that, I'm sure, given all their warts, still suggest that the interior high portions of large continents should be one of the first places where we would see evidence of an anthropogenically induced warming. And that's what we see here at over 5,000 meters on the Tibetan Plateau. I just want to point out that the types of projects that we conduct require international collaboration. We could not do projects in China and South America without our international partners. I'd like to move now from the Dunda ice cap here to the Galea ice cap in the western Kunlun. Galea sits at 6,700 meters. That's over 21,000 feet. And you see it here virtually in the clouds. But it has annual layering, and this vertical margin that you see tells us that it is frozen to the bed. This is the profile that one expects to see on polar glaciers that are frozen to the bed. And this is just a site of the drill camp. And again in this ice cap, these are the annual layers that have allowed us to count back. I want to point out that at 135 meters, we are still counting annual layers. We encountered late glacial stage ice at 153 meters on this ice cap. That should be the next slide. The ice cap's 307 meters thick. We essentially layer counted to right here, and we had estimated that we should encounter late glacial stage that's 12,000 years or older ice at 155 meters. We encountered it at 153. These analyses are still we're still making the analyses. We're halfway through. But what I want to point out is we have late glacial stage ice. This is the second time we've found late glacial stage ice on the Tibetan Plateau, but we still have half the thickness of that ice cap yet to analyze. So we anticipate that we're going to have a record of multiple glaciations. When we begin to put together a global array of records, we begin to see large-scale teleconnections. This is the accumulation from the Galea core, the last 1,000 years, compared to the Kelkaya core. And the similarity is striking. High accumulation, low accumulation. When you consider that the Galea sits on the far western edge of the Tibetan Plateau at 35 degrees north, Kelkaya sits 20,000 kilometers away across the Pacific Basin at 14 degrees south in the Andes. We know from current day observations that the El Niño Southern Oscillation dominates the Pacific Basin, and we also know that its variability is tied intimately to the monsoonal circulation system and the failure of the monsoons. We've proposed that the Earth actually has what we call mega El Niños, periods of time for hundreds of years in which the Earth operates in an El Niño-like state. We know El Niños today last 1 or 2 years, although in the last decade, El Niños hasn't operated quite the way we thought it should. The point is, once you begin to collect these records, you can begin to put these connections together. This is, again, a busy slide. This shows the 10-year averages for the last 1,000 years from 9 different ice core sites, all the way from South Pole Station to central Greenland and Camp Century. Maybe those people who would like to believe that the Little Ice Age is a global phenomenon might be disappointed, because what we see is that in Peru, the Little Ice Age was a very dominant feature. It's recorded in the Greenland cores. It's also recorded at South Pole Station, but we do not have evidence of the Little Ice Age in China. If you were to take 11 meteorological stations chosen at random but to give a global coverage, I suggest that you would not find coherences any stronger than these. It is very difficult to reconstruct climate from point sites, but that's what we have to do. The one feature that comes through very clearly in this record is the warming of the last century and a half. When we go places and drill new ice cores, we find that they often challenge our existing paradigms, the way we think about things. I want to return now to Peru, but go to northern Peru, to a site, Huascaran. We drilled here in this col at a little over 6,000 meters. The access was difficult. This is the drill camp in the col, and this was the second use of solar power for ice core drilling. To date the core, we again count annual layers. I'm showing you just 4 sections from the core, each section with the same 3 parameters used for dating: dust, oxygen isotopic ratios, and nitrate concentrations in green. This diagram shows the layer thinning with depth, and we thin essentially from a layer thickness of about 1.5 meters of water equivalent. Very quickly, we thin to centimeter scale. When we have this degree of thinning, we can generally, and if we're frozen to the bed, we can generally count on having a very long record. And in fact, we extracted from Huascaran, just in 1993, the first glacial stage ice from the tropics. I'm showing you now just the lower portion of the Huascaran core. And we see the delta 018 very negative. This shift from maximum or most depleted to most enriched is 8 parts per mil. Also, a substantial reduction in nitrate concentration of 2 or 3, and an increase of 200-fold in dust. The increase in dust, the decrease in nitrate, is very consistent with the climate that has been reconstructed, the late glacial stage climate shown on your right, based upon a variety of glacial geologic evidence and palynologic evidence. Essentially, at the height of the last glacial maximum, deserts were 25% more extensive. The area was much drier. The tropical rainforest, which we see here in dark green, was much less extensive, much more savanna. And the Amazon River ran in a canyon, a deep incised canyon that drained the moisture out of this basin very effectively. So the decrease in nitrate, we think, is associated with the reduction in vegetation. The increase in dust is associated with the increased frequency of aeolian features. Now let's compare the Huascarán record to similar records from both polar regions. On the extreme right, we have the Dye 3 record. This is dust, late glacial stage, high dust, depleted or more negative delta O18. This is Dome C. This is in central East Antarctica. Again, high dust for the glacial stage and much more negative delta O18. And then on your left, high dust in Huascarán and more negative delta O18. In fact, the delta shift from late glacial to Holocene conditions is 8 parts per mil on Huascarán compared to 6 parts per mil on Dome C and 7 parts per mil at Dye 3. Just point out briefly, also evidence for the Younger Dryas. During the deglaciation sequence, seen best here in Greenland, the warming was interrupted by a return to near full glacial conditions for a matter of 1,000 years or so. And Dr. McElroy will talk more about these type of rapid changes. But I want to point out that the Younger Dryas is also recorded on this ice cap at 9 degrees south. This is what I mean about challenging the existing paradigm. The existing paradigm with regard to tropical climate is that the tropics don't change much. And based on the climate reconstructions, the thinking was that the tropics during the last glacial stage were not substantially colder. This ice core record, along with records that are now emerging from corals and from some other pollen cores in the basin, challenge that and suggest that temperatures during the last glacial maximum were as much as possibly 5 degrees colder. We have to remember that the current climate models that are used to make future projections have been tested in terms of their validity against their ability to reproduce known conditions. The problem is the known condition to which their feet were held to the fire were not really known. And so these new cores tell us that we have a lot more work to do with the climate modeling. Finally, during the last 2 decades, it's important to recognize that ice caps and glaciers outside of the polar region, primarily, have been diminishing or disappearing at an astonishing rate. In the last few weeks, if you've been watching on your internet, you'll notice there have been the reports of the increased frequency of icebergs from the Weddell Sea area. But in reality, there have been other observations, such as the Warty Ice Shelf, which since about since the 1950s is now down to something on the order of 30 to 25% of its size just 3 decades ago. And for the first time in history this year, ships could circumnavigate Ross Island because the land bridge connecting it to the mainland has disappeared. The ice core record from the Dyer Plateau shows us, this is delta O18, shows us essentially that since the 40s, there has been a marked warming in this region. You might look back and say, oh yeah, but there was a warm time back then. The difference is not the degree of the warmth. The difference is that warmth sustained? And this is a 50-year warming period. Returning for the last time to Quelccaya, we've had the opportunity to observe in this area since 1974. And I have to use what used to be called the dirty word, the M word, that's monitoring. We were always told, in the ice coring business that we don't monitor, we just go out and get records. What we have found is that monitoring is critical. Just like the ice cores that provide this long-term history, we need to be monitoring now. We need to start these records, whether they're people will say, yeah, but if we start a satellite record, we're only going to have, in 20 years, we're just going to have 20 years. But that's 20 more years than you would have if you don't start the program. And I'll just show you the value of monitoring. On Quelccaya, in 1976, we drilled the core here at the summit, and you can see the beautiful preservation of oxygen isotopic ratios. At the same site in 1991, we drilled a core, and you can see that record is obliterated. It's obliterated by the percolation of meltwater. If we were looking at the Quelccaya ice cap today and trying to determine whether it had the potential for a long-term climate record, we would pass it up. This is the Coriolis Glacier. It's the largest outlet glacier on Quelccaya, and we have been able to get terrestrial photography that shows the retreat of that outlet glacier since 1963, 68, 83, 91. More importantly, this graph is the rate of retreat. From 1963 to 1978, it retreated at a rate of 4 meters a year, then 7 meters a year. And since 1983, it's retreated 14 meters a year. Finally, we just have basic observations. This boulder is about the size of this stage, and this ice cliff, which is vertical, this is Quelccaya again, I'm coming back now to that vertical margin, is about 20 meters high. And this picture was taken in 1977. This is 1 year later in 1978, 1983, 1989. This is the boulder now. This is the margin. And in 1993, this is the boulder, this is the margin, and it's 20 centimeters high. This is happening around the world. In the tropics and subtropics, the Lewis Glacier has lost 40% of its mass in the last 25 years. In the Ruwenzori, the Speke Glacier, they're all disappearing. The sad part is, not only is there an omen here that something is different, that these ice masses that have lasted for centuries are going away, that should concern us, but with them, they're taking these very valuable archives. So I hope that I have convinced you that ice cores offer a multifaceted